back propagation through time. This is back propagation in an RNN neural network. ठीक है, back propagation basically क्या करता है? It checks the loss function of all the nodes in the neural network and according to that it trains itself again. ठीक है, so अपने क्वेश्चन के अंदर दिया है एक्टिवेशन फंक्शन एज सिग्मॉइड एंड लॉस एरर फंक्शन एज क्रॉस एंट्रोपी. उसके हिसाब से वी हैव टू कैलकुलेट द लॉस फंक्शन. ठीक है, बट बिफोर वी डू इट फॉर RNN आई विल फर्स्ट एक्सप्लेन कि एक नॉर्मल बैक प्रोपगेशन के अंदर कैसा होता है. ठीक है, सो नॉर्मल बैक प्रोपगेशन के अंदर चेन रूल कैसे यूज़ करते हैं. सो नॉर्मल के अंदर अपना लॉस फंक्शन जो रहता है इट इज़ डेराइव्ड विद रिस्पेक्ट टू z एंड उसके अंदर चेन रूल कुछ इस तरीके से आता है. ना z जो है वो अपना इनपुट रहता है गिवन बाय हिडन नोड, राइट, एंड देन अपना जो y हैट रहता है वो अपना आउटपुट रहता है. ठीक है, तो अपना लॉस फंक्शन जो रहता है अगर अपने को विद रिस्पेक्ट टू z निकालने का है तो इट इज़ फर्स्ट डिपेंडेंट ऑन y हैट एंड देन द y हैट इज़ डिपेंडेंट ऑन z. दिस इज़ हाउ अ नॉर्मल प्रोपगेशन चेन रूल वर्क्स. ठीक है, अब फॉर व्हाट आवर क्वेश्चन इज सेइंग उसके हिसाब से जाएंगे. तो अपना क्वेश्चन बोल रहा है कि हम सिग्मॉइड फंक्शन यूज़ कर रहे हैं. ठीक है, सो अ सिग्मॉइड फंक्शन जो क्या होता है पता है, y हैट उसका जो रहता है विच इज़ इक्वल टू एक्टिवेशन ऑफ z एंड दैट एक्टिवेशन फंक्शन इज़ 1/1 प्लस e रेज टू माइनस z. ठीक है, इसका डेरिवेशन निकालेंगे dy हैट विद रिस्पेक्ट टू dz इज़ इक्वल्स टू y हैट अपॉन 1 माइनस y हैट. सो बेसिकली यहाँ पे क्या हो रहा है कि वी आर फर्स्ट डिराइविंग दिस विद रिस्पेक्ट टू z बट इसको अपन लिख रहे हैं इन टर्म्स ऑफ y. सो यहाँ पे क्या हो रहा है, राइटिंग डेरिवेटिव इन टर्म्स ऑफ y हैट. ठीक है, इसका डीप में स्टडी करने की ज़रूरत नहीं है क्योंकि अपना मेन मोटिव जो है वो RNN का बैक प्रोपगेशन देखने का है. दिस इज सॉर्ट ऑफ लाइक अ गिवन, लाइक अ प्रीरिक्विजिट दैट वी ऑलरेडी नो कि सिग्मॉइड एक्टिवेशन फंक्शन का डेरिवेटिव विद रिस्पेक्ट टू z इज़ y हैट इंटू 1 माइनस y हैट. ठीक है, नेक्स्ट वी आर गोइंग टू सी इज क्रॉस एंट्रोपी. ठीक है, मोर टू बी मोर स्पेसिफिक बाइनरी क्रॉस एंट्रोपी. ठीक है, सो बाइनरी क्रॉस एंट्रोपी का फंक्शन कैसा होता है, it is a loss function, so it is written by L is equals to minus y into log of y hat plus 1 minus y into log of 1 minus y hat. very easy to remember. ठीक है ना, इसका अगर अपन डेरिवेटिव निकालेंगे dl upon dy hat with respect to y hat, so what will we get? तो ये वाला जो पार्ट है y will remain as it is a multiplication एंड ये जो y hat log of y hat डिराइव होकर हो जाएगा 1 upon y hat. सिमिलरली यहाँ पे 1 minus y will remain as it is and log of 1 minus y hat will become 1 upon 1 minus y hat. ठीक है, ये हो गया. इसको हम कुछ ऐसे लिख सकते हैं माइनस से पूरा y इंटू 1 माइनस y हैट प्लस y हैट इंटू 1 माइनस y द होल अपॉन y हैट इंटू 1 माइनस y हैट. सो नाउ वी नो द डेरिवेशन ऑफ सिग्मॉइड फंक्शन विद रिस्पेक्ट टू z and the derivation of binary cross entropy loss function with respect to y hat. और अपना original chain rule of a normal back propagation says dl upon dz is equals to d L upon y hat which is this. तो अपन इसको ऐसे लिख सकते हैं माइनस वाई इंटू वन माइनस वाई हैट प्लस वाई हैट इंटू वन माइनस वाई द होल अपॉन वाई हैट वन माइनस वाई हैट. ये पूरा यहाँ पे ले लिया एंड देन मल्टीप्लाइड बाय द डेरिवेटिव ऑफ वाई हैट विद रिस्पेक्ट टू z, जो कि हमने यहाँ पे कैलकुलेट किए हैं. दैट इज़ वाई हैट इंटू वन माइनस वाई हैट. नाउ वी कैन सी ये और ये कैंसिल हो जाएगा एंड दिस विल गिव अस नथिंग बट वाई हैट माइनस वाई. इसको सिंप्लीफाई करेंगे सो विल गेट वाई हैट माइनस वाई. कर लो, अभी सिंप्लीफाई कर लो. क्या मिलेगा? वाई माइनस वाई वाई हैट प्लस, यहाँ पे प्लस आएगा एंड देन वाई हैट माइनस वाई वाई हैट. सो ये कैंसिल हो गया. सो वी गेट ये माइनस हो गया वाई हैट माइनस वाई. तो ये मिल गया आपको. ठीक है, अब ये अपना बेसिक वाला हो गया. नाउ वी विल कम टू सी कि हम RNN के अंदर कैसे इसको अप्लाई करेंगे. ठीक है, now we will see the basic architecture of RNN. So these S are hidden nodes, X are inputs and O are outputs, and these are all on some time steps t minus 1, t plus 1 and so on. And now you can see there are three types of weights that are used in an RNN. X, when sent to the hidden node, uses U as a weight matrix. The previous S node sends its output with a W weight matrix, and our current, or any, you can pick this or this as a current hidden node. Your current hidden node sends the output with a V hidden matrix, weight matrix. So we have three weight matrix. U is input to hidden, then W is hidden to hidden, and V is hidden to output. Now to back propagate through this RNN, we have to derivate each and every node with respect to all three of these weights. And that is what our question is going to be. Our main objective in back propagation is going to find these three, that is loss with respect to W, then loss with respect to U, and loss with respect to V. Now the propagation in the RNN works using these two functions. To propagate from one hidden node to the other hidden node, we use these two weight matrix. As the first equation says, Si means S at any time step is the activation function sigmoid we are using here. U into X, that is our input multiplied by the weight matrix associated with that, plus W into Si minus 1, W into the previous hidden node Si minus 1, plus a bias. Similarly, to now give an output upwards, this was just to give a input to the other hidden node, right? Now to give an output upwards, that is our O, or we can also call it Y, we use activation function V. V is the weight matrix associated here, into Si means the hidden node at that time step, plus another bias. Now it is important to note that all three of these remain the same throughout. we do not assign W1, W2, W3, U1, U2, U3, V1, V2, V3. No. W, U and V remain the same throughout the RNN. To start to find these three, we'll start with loss function derivative with respect to W. Now we can see W is in SI, right? So that SI has our hidden to hidden weight W. dl theta upon dW will be equal to dl theta upon dSi into dSi upon dW. Because the loss function is not directly related with W, loss function is related to our SI function, and the SI function is dependent upon our W. Now we will have to calculate these two separately. Now we have already seen over here in our given and a prerequisite section that dl upon dz is equals to y hat minus y. So our dl theta, that is loss function with respect to our activation function, will be equal to y hat minus y. Now it's time to find our activation function with respect to W. Okay, now this is very complicated, but once you understand it will be easy. Here we are using a sort of chain rule that's called as a multi-variable chain rule. Now see, what we are saying is we have to derive this function with respect to W. So our SI is equals to ux plus W SI minus 1 plus B. Right. Now if we derive it with respect to W, derive it with respect to W, then we are going to get SI minus 1. But we can't just write SI minus 1 because SI minus 1 is equals to ux plus W SI minus 2 plus B. Now in SI also we have a W. Similarly, SI minus 2 is also going to have W. So this will keep on going, and then we have to use the multivariable chain rule, which suggests that dSi upon dW is equal to summation of k equals to 1 to n dSi upon dSk plus d. This plus suggests there are going to be multiple of these keep on happening, plus Sk upon dW. In a simple format, we can also think of it as if, assume we have 3 nodes. Okay, so derivative of S3 with respect to W is going to be derivative of S3 upon W plus derivative of S3 upon derivative of S2 into derivative of S2 plus upon dW. And then derivative of S2W is going to expand just as this did. It's going to be like derivative of S2 upon derivative of W into derivative of S1 upon S1 over here, S1 upon W. So this will keep on happening, but the main thing to remember is that derivative of SI with respect to W is written as such. So our final answer will be derivative of L theta with respect to W is equal to y hat minus y multiplied by summation of k equals 1 up till n, derivative of Si with respect to derivative of Sk into derivative of Sk upon derivative of W. This thus suggests that it is a multivariable chain rule. So now one of our weights is already solved. Now we have to move forward to our next weight matrix, that is U. Now we can see that U is also in our SI function, and U is our input to hidden weight matrix. Okay, now similar to what we did for W, dl theta upon du will be equal to dl theta with respect to dsi into dsi with respect to du, and we already know this is equal to y hat minus y. Now what is this? So dsi upon du is equals to, we will write our function here, ux plus wsi minus 1 plus b upon du. Now if we derive this equation with respect to u, we will get x, as both of these will go out as constants and u will become 1, so only thing remaining is x. So now we can write it as dl theta upon dw is equal to x. Yeah. Now our third and final weight matrix that remains is dl theta upon dv. V, as we can see, is not in SI, it is in YI, and it is our hidden to output weight matrix. Now this is a little different from these two, so please pay attention. This, as usual, will be equal to dl theta upon dyi into dyi upon dv. The difference you can see over here is, in the previous two we used dsi. It's because the weight matrix were in SI equation, but this time the weight matrix is in UI equation, which is our output equation. So we will use yi here, or you can even use O. Either is fine. So now as we already know, this is going to be y hat minus y. Oh, my mistake, यहाँ पे आएगा y hat minus y into x. So this is y hat minus y, and then we have to find what is dyi upon dv. So dyi upon dv is equals to d of activation function of vsi plus c upon dv. We are just going to write our equation here, and now we have to derive this equation with respect to v. Or as we can see here, there is an activation function. So this activation function is our sigmoid activation function. Derivative of sigmoid function, say suppose sigmoid function of x, तो उसका derivation क्या होगा? Sigmoid of x into 1 minus sigmoid of x. This is the derivation of a normal sigmoid function. But now inside the sigmoid function we also have another equation. So the derivative of inner function will be d upon si of vsi plus c, which is going to be si. No sorry, यहाँ पे dv है, करेक्ट. डेरिवेटिव विद रिस्पेक्ट टू v, सो अपने पास बचेगा si. All of this will go in constant and this will become 1. So now our final answer dy upon dv is equals to y hat minus y into the outer sigmoid function into si, where x equals to this wala equation vsi plus c. So now we can write it in our answer as such: dl theta upon d, यहाँ पे u आएगा, d आएगा, is equal to y hat minus y into activation of x, 1 minus activation of x into si, where x equals to vsi plus c. So this was our back propagation through time.